want to talk about monetary policy for proof-of-stake blockchains, and I'm going to use sort of traditional tools from macroeconomics to do that. Okay, they've adapted a little bit. So I'm going to start with motivation. Again, it really follows closely what we've seen. So this is Ethereum staking ratio. It's the share of Ethereum that's staked in the total money supply. It's been going up mostly. There's sort of multiple interpretations of this. One is that this is good news because it improves economic security because there's more staked. Another view is that this is expensive, and it's the mechanism we saw. This is paid for mostly with newly created tokens, seigniorage, and that acts like as a tax, and that tax is discouraging so the tax that it primarily affects those that are not staking, and it discourages use of Ethereum in the unstaked form. And so I want to have a model to study this trade-off between security on one side and dilution, or security or money creation or liquidity. And so it's going to be very simple model, and so the most simple model I can think of that is at least dynamic, and it's an equilibrium model. Okay, and there's four variables or quantities in this model. There's money. There's two types. Okay, there's a token. A token can be used, MU, money used, or it can be staked. Okay? So there's the choice between the two. When the token is staked, the only thing that happens in this model initially is that the staker receives rewards. There's no other direct cost, and for now the liquid staking, or this will postpone it for a while. So just forget that there's such a thing as liquid staking for a while. There is an equilibrium price. Okay, so this is the price of the token in dollars. That's determined in equilibrium, and then there is the staking reward yield. Okay, and that's the percentage compensation that's paid for staking. Think of this as that's the policy variable. It's the protocol that controls that, possibly through a policy rule, or some more flexible specification. Okay, so this is the model. So it's a dynamic model, DSG type model. It's a representative agent type. So there's a lot of agents, but they're all the same. They're atomistic. It's a small open economy. Okay, so this is the idea that each blockchain is like a separate country. It has some influence from the outside, but it's small enough not to influence the rest of the world. And so in this economy, agents they pick money used and money staked. Okay, that's a portfolio problem. There's also consumption, but that doesn't really play a role here. It's just the numeraire. Okay, so all the prices they're in dollars. Okay, that's the reference currency. And so every period, agents enter with some holdings. So this is the amount they've staked, the D for deposits, the amount they were using. That's the price, and they reallocate. Okay, they decide the quantities to stake and to use. Money is useful. Okay? It's the money used. It enters through this sort of money and utility function. You can call this real balances. Okay, it's the real value, the dollar value of this, or you can call it liquidity. Yeah. And so that's the optimizations that agents face. And there is a money supply. That's the aggregate sort of, just the supply, that the total money you're starting with, it gets increased by the issuance from staking, and this is at the end of the period that's available for going forward. So the simplest deterministic case in the equilibrium in this model is just three equations. I guess it's again the supply equation, and there's two pricing equations. These are the first order conditions, the optimality. Okay, the price from a staking perspective, the price is equal to the expected value of what you get. Okay, so this is discounted. That's the price tomorrow. That's the staking return. And from the users, instead of getting the staking yield, the user gets the marginal utility. Okay, so that's the convenience yield from money. Okay, so this is the model now under very general assumptions, just making this decreasing, okay, decreasing marginal utility of real balances. The solution of this is just in the stationary case, okay, stationary equilibrium, meaning that the policy rate, the issuance yield is kept constant. This is what's going to happen in this economy. Okay, wherever we start from, so initial money distribution, immediately the equilibrium, it jumps to this staking ratio. That depends on just the discount factor. Again, that's, you think of this, the required rate of return, and then the issuance yield. Okay? This is a bit like supply curve of stake. Okay? It tells you how much is staked in equilibrium as a function of the rate that the protocol offers. And so this is, again, obviously it's very simple. Yeah, so we have this constant staking level, or sorry, ratio. The economy is not totally stationary. Money is growing here. Okay, so money is growing, and the price is moving in the opposite direction in percentage-wise. Okay, so one thing you can do is you could just sort of plot this here. So here I plot the blue is this curve, right? Sort of as a supply curve. So here's it's the yield as a function of the share. And I added a bunch of dots. See, these dots correspond to the 20 largest proof of stake blockchains. You can see sort of how they line up. Now, obviously, this is not, don't expect this to fit perfectly. I think what's nice is that the larger chains, which we think some are more stabilized on this, they're pretty close on the line. Okay, so what does it say really? Okay, so these, of course, they're all different. They're all paying different staking yields. Okay, but in this model, what sort of happens is, if you take the first order condition for staking, just rewrite it. It says there's a required rate of return, and that have to satisfy that with two components. There's the staking yield and the price change. Yeah, and yeah, you had a Carol.
If you were doing this, why wouldn't you make the yield depend on the amount of money in the system at each point in time?
It will come. That is just, that go slowly. Okay. This is, for now, it's equilibrium, no policy yet. So absolutely. Thanks for clarifying this. Okay. Yeah.
Suddenly yield is not indexed by T.
That's right. So this is so this is what I've started. This is stationary case. Okay. It's just it's the most simplest, just to sort of show what happens. The most boring example. Okay, they get more interesting in a moment. But sorry for going slow. Okay, so that's it. So what it says in words, if you believe there is some regularity here, that the points are sort of lining up at least a little bit along the lines, what it says is that there is a required rate of return in the model. This price change, you know what it is? It's just money growth. And then the money growth, you can also link it to the staking share and the yield. And then this says basically there's this is the dilution adjusted return, and it says roughly equalized across blockchains. Okay, some blockchains they pay more, but you get diluted more. Now obviously this is very simple. Okay, there's tons of stuff missing. There's no risk, no growth, no fee income, and so on. Okay, so this is just really a first approximation. Okay, so let me get to policy. Okay, so now thinking about what we want to do with this y, the yield. Okay, that's the policy variable. And so to study policy, I need to add something. I need to tell you why staking is useful in this model. Up until now, it was not useful. It's just spending money. Here it becomes useful. Okay, so I think there is a staking target. D star from a security perspective. Okay, that's sort of the optimal, and there is a utility cost for deviating from that optimal. And what enters here, this is the aggregate staking ratio. Okay, it's not the individual one. So agents don't internalize their impact on this. Okay, so that's the objective. So a policymaker, okay, the protocol that wants to design an optimal policy is gonna maximize this utility function, okay? And it's gonna try to control and use in a number of ways. 10 minutes, thanks. Okay, so the first case, again, I'm going slowly, okay? So the first is a simple case. What's the optimal constant staking yield? Okay, so you want to have a constant yield, but you want to put it so as to get the highest lifetime utility. So it's the sum of these. For the log case, okay, this utility function, you can solve it, but the key point is that the staking ratio we see, it's below the target. Okay, that's to say we're not bringing the blockchain all the way up to the optimal security level. Okay? I think the intuition is very clear why you want to do that is because there's these two things that matter: liquidity, real balances, security, and we're having this one instrument here, and we're never going to drive the marginal utility of this to zero, and so this is not going to go to zero either. So we're not going to close this gap, and I guess intuitively that's sort of the trade-off you have in mind. There is, we're not going to be perfect here. We're just going to trade these off, and the parameters are going to decide where we are or where we end up. Yeah.
I think I missed something very simply. So you're saying security, but where's the security in the primitives? Like if you go back to the consumption, the optimization problem that the user is solving, like there's no risk here that the blockchain fails.
Yeah. So
right?
So of course there's many different ways of how you could sort of introduce security as a one. I guess So one way you could do it, I guess maybe that's what you have in mind. There's some probability, there's some failure or some loss, and that could be a function of this. Yeah, that's an alternative. I'll start with this. I think it's much more transparent. Yeah, and that's it. But you can for a number of the things, not all of the results, but for many of the things I've done, this is it's not going to make a difference. Now it is true it's not separable. Yeah.
But I'm saying, imagine a world where the block. So can you just go back to where the user optimization problem was?
Okay.
Yeah.
The user.
Yeah, the preference structure, basically. So I'm saying, like, if I imagine,
what am I doing? Yeah, I got it wrong. I'll get that.
If I imagine a blockchain that is guaranteed to be secure, so I don't have to worry about any kind of reversion, anything like that. Like this preference structure doesn't.
The users do not. They don't take it into account at this level. Yeah.
Like, I think about security. I'm thinking about like precisely the point that Emiliano, for instance, advocated for the RFS, where they like explicitly blockchain can get reverted, so the preference structure takes into account that if the blockchain gets reverted, I don't get my payout.
So the users, they're not happy. Okay, they suffer from the lack of security, but it's not interacting with the rest. That's fair.
I see that you're getting about that, but I guess what I'm saying is I think that the narrative you're giving isn't true to the preference structure that you have, because I see that, like, yes, it matters for the preference.
It's an individual user does not internalize this. So the choice, if it's separable, then it doesn't matter. Okay, I can start without it, and it's.
I'm making a different point. What I'm saying basically is that your model doesn't allow for the fact that, for instance, I get nothing if the blockchain is successfully attacked. And so what I'm saying is, like, I agree with everything you're saying from a mathematical perspective, but I'm saying, because you don't have in your preference structure that I could like get paid nothing because there's attackers.
Yeah, the attack is not micro model what exactly an attack is and what it happens. There's just a cost. The cost is that if the security is not good, the agents that live in this blockchain economy, they're not happy. Okay, but they're not directly internalizing that they're sort of responsible for that. They just see the blockchain not working well.
Okay, I guess something is there might be other stories that map to exactly this thing, but yeah. Okay.
I agree. There's other ways to have it. I mean, again, I'm not saying, and I've done other things. This is just, I think the advantage of that is it's very simple. Okay, we see what it is, the objective, and then we can sort of take it from there. But it's not obviously it's not the only way to think about security or the lack thereof. Yeah. All right, so this is the policy with the constant rate. It's just a static trade-off. Intuitive, what do you expect? Okay, then I'll go to the next. The next level is to say, well, this is unrestricted policy. Okay, so now the protocol can decide to pick the whole sequence of rates. Okay, not just the one numbers before. And when I assume there is commitment. Okay, this is called Ramsey policy, and that's it's sort of it's a benchmark that's sort of widely used for tax policy, monetary policy. And so this is it's get the best utility as of time zero with full commitment. Yeah. Now this is it's not necessarily realistic, okay? But this is the best you can do. Yeah, so that's why it's a useful benchmark. So this is the way this works. Okay, so we'll just now we maximize the whole sequence. This is the Ramsey allocation, and so we do that because that you know, this is what the planner does, and the equilibrium, the equations we've seen, those are constraints for this maximization problem. And now the solution is going to look like this. Yeah, so for sort of reasonable parameter ranges, you cannot use a log here. That doesn't work. So this has to be different from 1. But now the long run outcome is that we're closing the gap. Okay, we're going to go fully security is at the target. So that's going to be optimal. And the way the policy is going to go, we're starting from below. So here that the target was set at 20%. So that's the best. Yeah, that's sort of a security target, and we're sort of approaching from below. And we only get there in the long run. Why do we get this? As it's these problems or solutions are usually a bit non-intuitive. Yeah, so why is it going to look like this? Let me give you some intuition. Okay, I guess I don't have too much time, so we're not going to get it all done. Why is there a transition? Why is it non-stationary? Why am I not staying constant? I think that the way to think about this is the objective is to maximize these paths, these trajectories. This is the instrument. This yield, and so the constant yield policy is just picking one number to maximize these paths, and that's just not flexible enough. Okay, that's just not a good enough use of. It's not very powerful. Yeah. The other thing that's special about these problems is that the initial period is different. Time 0 is different because there's nothing to be committed to. Okay, because there was no past. Okay, commitment is sort of implementing what you promised in the past, but at the beginning there's no commitment, and so at the beginning the Ramsey planner wants to use that degree of freedom, and it's gonna use this to surprise or to do something. And typically here it means you're gonna go to some higher or lower level that then helps you get the best outcome. Why do we close the gap fully? This is a bit less intuitive. Okay, again, but need to go through the equations. Let me give you the short version. Is that at the steady state in the long run, you can think you're picking only one thing. It's the staking ratio you want to end up. And at that point, when you're at the steady state, there's no more liquidity benefit. So you can move around the staking ratio. A net liquidity benefit, there's no change. The only things that changes is security costs. So you don't want to have any security cost left. So you're going to move that to the optimal. Okay, that's the story. Yeah. You want to know more, you know, it's in the paper. Let me show you what you can do with this now. Okay, so this is now I can make it stochastic. Okay, so we're going to add some shocks. Shocks, you can think of there's 2 shocks here, interest rate shocks. So that enters through the discount factor. Think of this as US. These are just US Treasury rates. And then we have staking convenience shocks. Okay, this sort of links it what we've seen before. I think there's changes in the protocol that make staking more attractive or new, new innovation. And so see what's going to happen here. Now what you can do is you can see how the economy under the optimal policy responds to these shocks. And to make it interesting, we can compare it to some policy rule that have been used. Okay, so this is something that's very close to what Ethereum has been doing. It's a square root function. It's on the ratio, not on the level. Okay, but that still it has the same properties when not a lot of when staking is low, the yield is high, and when the staking is high enough, it goes down. So let me show you some of the experience. 1 minute. Okay, thanks. So this is the staking convenience shock. The red is the shock. Okay, so staking all of a sudden has additional benefits. What it does, the green is the square root curve. Staking goes up, okay, because it's just better. And the curve is responding by lowering, okay, so that stabilizes it somewhat. But compared to Ramsey, that's the optimal policy. And so you can see that optimal policy, it responds significantly more, and the staking, the ratio moves a lot less. So here the square root curve, it gets it right qualitatively, but it's not enough. So you want to lever it up a bit. The interest rate shock is here. So interest rates go up. That's bad news for staking because the opportunity cost has gone up. And so here the staking declines. Okay, so that's the square root curve. There's some compensation by again, that happens through the curve. Ramsey is going to, again, respond much more aggressively. And here is going to keep the staking share entirely constant. Okay, so this is the type of shock a Ramsey planner would want to absorb. And I think this is related to this sort of result in the long run. Okay, this type of shock is not affecting the trade-off between the two types of investments, and so the security, you want to keep it stable. Again, the overtime. We leave it at that. Thank you.